So it's my pleasure to introduce Dr. Ryan Rhodes. I've conveniently been given a little script, so I'll start with that. Right? So Dr. Rhodes is a neurolinguist whose research is at the intersection of theoretical linguistics and cognitive neuroscience. He received his PhD in linguistics from the University of Delaware, where he worked as a lab manager for Arnold Hestedick's psycholinguistics ERP lab, and an MA in linguistics from Fresno State, where he worked on the Chukchansi, wow, how do I say that? Chukchansi Yokuts language documentation project. His current work combines electrophysiological and behavioral measures to investigate mental representations of linguistic structure, auditory prediction, and rule learning. And I'll add to this that Ryan's been a tremendous contributor to our undergraduate classwork. He's one of our most popular instructors among the undergraduates, and he's been really essential to the growth with quality that we're trying to ensure within all of our pedagogical offerings. I also wanted to say that Ryan's somebody I see almost every day, and he's been a major contributor to the intellectual experience of being at Rux, including for me. And it's been wonderful to have you in talks and to see you in the hallway. And it brightens my day to see Ryan. And if you all were here, you could brighten your day too. With that, take it away.
Nice guilt trip, John. Actually, I'm laughing a little bit because the last talk had a lot of palletization, depalletization, and I keep hearing this. So this talk is going to be a lot about phonology. I keep hearing depalletization is depalatalization, which is like a phonological thing. Do I have a remote control, or do I just push the buttons on here? Okay, just push buttons. So yeah, so I want to talk about using formal learning theory, using formal grammars as sort of a theoretical construct to investigate how people learn, how people represent certain kinds of patterns in the linguistic domain. And there are lots of questions that sort of fall out from this. But one of the things that we kind of push in cognitive science, especially here, given I think our sort of intellectual history at Rutgers, is that we tend to lean heavily into computational theory of mind and thinking that since computers are just things that compute, human beings are basically computers. The mind is a computer. So if we take this approach, we say minds are computers, then the relevant question becomes, what kinds of computations are we doing? That's really the only sense in which that's an interesting avenue for thinking about cognition, is to think, if I'm a computer, what exact kind of computations am I doing? So we can think about this in the linguistic domain. What kinds of computations do human beings make when they process language and when they learn language? So I'm going to talk about just a couple of studies, but it sort of outlines a kind of research program that I'm interested in that's at this intersection of formal learning theory, using tools from formal learning theory and formal grammars, and laboratory phonology, doing things like teaching people artificial languages, and neuroimaging to see how this stuff is potentially neurally implemented. So this is my outline. I'm going to talk about, we got to talk about some formal grammar stuff and try to keep that kind of light. But it leads into the thing called the subregular hypothesis, which is a hypothesis about a certain kind of mental modularity, right? That we have some kind of modular computational machinery for doing very specific kinds of computations. We want to be able to describe what those computations are and sort of what the limits of that space is, what the limits of that module are. And I'll talk about some specific studies that we've done. These are things that I did at University of Delaware, but we're working now, I'm working with a bunch of undergrads. Russell's here, he's in my research group. We're working on new stuff that we're going to do to push this forward, and that'll be the last thing I talk about is where do we take it from here. So first, I just want to talk about linguistic patterns in general. Like, what are the kinds of computations that people do when they speak languages, when they learn languages? To do that, first you have to talk kind of about what language is and what it looks like and what the patterns are. So actually, I used to teach linguistics classes before I came here because I was in a linguistics department. And when you teach intro to linguistics, very, very common to get questions like, what language is the most complex language? Is Estonian more complex than English? Is Tamil the most complex language in the world, or Hungarian or whatever? And we always have to say, we're like contractually obligated to say, all languages are equally complex. All languages are equally expressive. We don't really want to entertain a lot of questions about complexity. I definitely don't want to compare complexity between languages. And part of the reason for that is that languages are really diverse sets of stuff, of like patterns. and all of the different patterns that you can group into a single language like English. There are like tons and tons of different patterns within English that are all different levels of relative complexity. So it's really hard to assess the complexity of a single entire language. But we can use this hierarchy that Noam Chomsky came up with. I think like in the mid-50s, Chomsky started doing this work, creating descriptions of formal languages. We can actually use this to chart complexity to some extent. We can see that human language occupies sort of like broad swath of this that goes from kind of the simplest possible patterns towards the top. Gets a little bit contentious as the higher up you go, like people argue about whether they have or have not seen patterns that fit this description in like some individual languages or not. But it's pretty uncontroversial to say that it's definitely in regular and context-free areas of this hierarchy. Can also chart other things onto this hierarchy, like animal vocalizations, which tend to be a lot simpler than human languages, or music, which also tends to be a little bit computationally simpler than human language. But for the purpose of this work, I want to focus just on one domain of human language, which is sound patterns. So not going to think about syntax, not going to think about how sentences fit together or whatever. We're just going to think about sound patterns. So the sound patterns that govern what a valid word can sound like in your language. And that's all going to fall in this shaded area here. It's all going to fall in this in relatively lower regions of this hierarchy. Okay, so before we get into this too much, I want to just do like a little game, which is, this is another thing that used to come up when we teach linguistics. People would also ask us another very common question. Why should I get a linguistics degree? What can I do with a linguistics degree? And I never want to say like, I don't know. I don't know if you can do anything with a linguistics degree. Choose something useful like engineering. So sometimes we would say things like, well, I don't know, like, pharmaceutical companies, they're always coming up with new drug names. I don't know who comes up with those, but like, maybe it's a linguist, could be. Maybe you can do that. This is a thing I would see on like brochures too. It's like, why get a linguistics major? Is there things like marketing or coming up with pharmaceutical drug names? So let's do that. Let's think about, let's say, we've been hired by some pharmaceutical company like AstraZeneca or something, and we have to come up with names for drugs. What would be a good name for a pharmaceutical drug? You can just like yell out anything right now. It's hard to come up with words on the spot, huh?
Ryan X.
Ryan X. I like that one. That's good. It sounds relaxing. I don't know. How does this sound?
It doesn't.
It doesn't. Here's a question. Since all of you in the room speak English, how would you pronounce this drug if it was offered to you? Psychosoma. Yeah, does that sound right there? Nobody's going to say psychosoma. Or something like this. Is anyone going to say Sorcon? Maybe, I don't know if it comes through with the mass, but like definitely we're not pronouncing the P, right? I think most of us are going to opt for like just ignore that altogether, right? It's like the little kid in the old Roadrunner cartoons say, when I grow up, I want to be a psychiatrist. You're like, the reason that's funny is that it violates some very basic rule of English that says don't do that. There's something in English that says, don't have a word that starts with a PS. I don't like that. And when I'm presented with it, I want to fix it and like just. So the question is, how do you describe what's actually happening? How do we describe this pattern? How do we describe what this rule actually is? Once we talk about how this might, how to describe it, then we can talk about how do you actually learn it. But we're going to use some formalisms here. We're going to, the formalisms of formal grammars and formal languages. So one way you can describe this particular pattern, the thing in English where you can't have a P and an S at the beginning of a word, one way to describe this is using strings and substrings. So you can think about a word as being a string. It's like a string of symbols. You can think about it as letters. Linguists usually don't like talking about letters because it doesn't map very well to like the actual mental representations or the sounds or whatever. So maybe it's better to think of these as encoding sounds. But anyway, it's just going to be some kind of linear string of symbols. And what we can do is we can sort of pull out substrings, right? So we pull out little adjacent segments, little segments of adjacent symbols. And here you can see I've sort of highlighted the PS as like the thing that I don't really like. So something you could do is you can take a string like this and you can actually just explode it into like all of the possible substrings that compose it. right? And we refer to this as a K factor. K factor here is how long of a substring are you gonna look at? How much of this are you gonna pull out at one time? So if I'm looking at substrings of length 2, it's K factor of 2. These are all of the substrings that I can pull out from this word. There's quite a few because I need every combination. So PS, SO, OR, RC, CO, ON. Those are all of the substrings in just this word. Now the question is, how do I figure out if the rule has been violated here, the rule of don't have the PS thing? Well, it's pretty straightforward, right? If the rule is don't do PS, then all I need to do is pull out all these substrings and look for a match, right? So I have like this little list that says, make sure you don't find this stuff. I check on my list and I look in the word and say, aha, there it is. So this word is no bueno, I don't like this. So this explains a little bit about how you might be maybe mentally representing a rule like this, of this type, and also how you might detect violations of the rule, which is something that happens all the time if you're speaking a language, right? You need to know if the things you're hearing are valid in the language that you speak, or if you need to do some kind of repair. So this works for English. These words are going to wind up being kind of bad for English. We have to do some kind of repair to make them pronounceable. How do you feel about these names? Does this one work for you guys? Are these pronounceable? Spellings are kind of funny, but Shingrix, is that okay?
Makes you sick for the weekend.
Huh?
Makes you sick for the weekend, Shingrix.
Yeah, these are all real drugs, by the way. I looked this up on a drug database. I didn't make these up. I think this one's for psoriasis. This one is some kind of performance enhancing drug that makes you concentrate. That's like now illegal in most countries outside of Latin America. And yeah, this is a shingles vaccine. Shear-descends is some kind of tooth enamel coating, fluoride coating or something. But these shouldn't really like ping us as sounding bad. They sound totally fine for English speakers. But we would not be having this intuition if we spoke Navajo or Chumash. We would be sitting here saying, that's terrible and I won't say it. I refuse. Because Chumash and Navajo have a very different kind of rule. It doesn't say something like can't have a P and an S. It's a little bit different. And I want to see if we can figure out what the pattern is. So I'm going to do some Ling 101 homework here. Here's our data set from Insignio Chumash. This is a language spoken in California. And we have a whole bunch of stuff here, a whole bunch of words, a lot of morphology going on. We got words like shapit sholik, sapit solus, shapit sholushwash, hashintilawash, sistisigepus, and kushoshoyin. So let me just ask the room, is there a pattern here? Is there a detectable pattern? This is a big ask. Yeah, so this is also written in an International Phonetic Alphabet, which maybe everyone's not familiar with, but shapit sholik, sapit solus, shapit sholuswash, ashkintilawash, sistisiyepus, shushoyin. And there's something going on with the S and SH, right? So you've got words that have a whole bunch of sh, shapit sholuswash. You've got words that have a whole bunch of sa, sistisiyepus. And curiously, what is there not one example of here? What are we missing? There's not a single word that has an esh and an S in the same word, right? So words are like totally homogeneous. You can either have eshes or you can have s's, and you cannot have both. So if we go back and we look at those drug names that seem totally fine for us, would be totally inappropriate in a language like Navajo or Chumash because you can't have sh and xa in the same word. You can't have sh and then sa and za in the same word, even though they're really far apart from each other. So the English pattern is perfectly local, right? It's just one sound to the next adjacent sound. But there's something else entirely happening in Chumash and Navajo where it's not, there's a rule, and it's about what kinds of things can appear in a word, but it's not just what can appear right next to each other. It's, these are the things that can appear in a word, and I don't care how far apart they are, it's gonna get on my nerves if they're anywhere, even in the same domain. So it's a very different kind of pattern. The question is, how do you actually compute this? And it turns out that just having a little list of prohibited substrings is not gonna do it. It's not computable in the same way. So you need a different formalism. The formalism here, instead of thinking of substrings, we're going to think of subsequences, where substrings is just pulling out a little, two adjacent symbols from your string. Now we're going to say, you're going to pull out two symbols, but they don't have to be adjacent. The only thing that matters is that they have the right relative order. So I can't have a sh and a x, even if there's a bunch of crap in between. That doesn't rescue me from violating this rule. So now if you want to figure out if a new string is violating this rule, or if it follows the rule, you have to do something a little different. Now you have to pull out all of the possible subsequences. And again, we can define a k factor, right? So maybe we want subsequences of length 2. That's just pull out two things that maybe have some distance between them. And so we're going to wind up pulling out things like sh-e, sh-n, sh-g, sh-er, sh-x, e-n. There's actually a huge list. I didn't write the whole list because it goes on and on and on. Because you have to have sh followed by this, by that, by that, by that, by that. Then e followed by this, by that, by that, by that, by that. And you got to do that for every symbol until you've exhausted everything. So it's a bigger list of stuff. The upside is that once you do that, then you can figure out if the rule is being violated, no matter how far apart the things are. So again, you're doing the same basic computation here. You've got your rule, which is just a little list of the stuff that's prohibited, and you're going to look for those prohibited subsequences in any new word you hear. So here's our violating subsequence. Making sense so far? The interesting thing here is that these patterns are, they occupy different levels of complexity in this complexity hierarchy. So the English type patterns, this is not just English has this, lots of languages have this. English has it, Spanish has it. Spanish has a very different way of fixing it when they get words that violate it. English has a tendency to delete things like P. Spanish has a tendency to add a vowel. So just a different strategy for rescuing this stuff. And then you have this slightly more complex pattern, the sibilant harmony pattern from Navajo and Chumash. And to my knowledge, those I think are the only two languages documented with this specific pattern. But there are similar kinds of patterns like vowel harmony in Turkish, which maybe some people are familiar with. So this is the interesting thing, is that it seems that every type of pattern that's ever been observed that we can describe in terms of like sound patterns in human languages, they all fall not even just within this larger region, but within these smaller subregions of the regular part of this hierarchy. So it's very limited space that all these computations inhabit. So I'm going to turn and talk about what this means in terms of how our minds actually work. And there's a really interesting hypothesis called the subregular hypothesis that this is sort of pointing towards, which is all of the computations that are being performed in this domain in terms of sound patterns of languages, in terms of like trying to figure out what a valid word can sound like, they all fall within this really narrow region underneath the regular region in the hierarchy. And we can subdivide that regular region into a couple of subregions, right? So we have the strictly local. Those are the things defined with substrings. And we've got the strictly piecewise defined with subsequences. And they both fall under this non-counting region, which we can actually define a third pattern, which I haven't brought up yet, but we'll talk about now. So we've got this very simple English adjacency pattern, can't have P followed by S. We've got this slightly more complex Navajo pattern of if you're going to have an S, they've all got to be Fs, no matter how far apart they are. And then we've got this pattern, which occupies a slightly higher region, this non-counting region. And the rule here is the first symbol has to match the last symbol. And it doesn't matter what happens in the middle. So it's a little bit different. I can get something that has S, Esh, S, which would be bad for Navajo and Chumash. But it's fine for first last harmony, just harmonizing the first and the last. The interesting thing is that no language does this. So we have like this nice boundary where it's like, we've got strictly local, we've got strictly piecewise. Going up even one step into the non-counting seems to be a no-go for human languages. And this raises really interesting questions like why this is the case, why this is so highly restricted. But right now we're just focusing on like making sure that these are in fact the boundaries and finding out exactly whether these types of things are learnable or not. So this is the subregular hypothesis in a nutshell, that we have some kind of dedicated phonological learning or phonological processing module that is hardwired to learn strictly local and strictly piecewise patterns, but it's not really equipped to do anything more complex than that. It's not equipped to do non-counting. It's not equipped to do anything further up the hierarchy. And there must be some kind of neural implementation to this. We don't know exactly what it is yet, but we think it probably is happening. If I had to guess, it's happening somewhere in this phonological network in STS, in mid-posterior STS, but it could be more distributed. We don't know yet currently because there hasn't been enough work done on neuroimaging with this type of learning. But I want to highlight one study that was done that was sort of like the springboard for a lot of the artificial grammar learning stuff that we did afterwards. This was sort of like the first pass at an artificial grammar learning study to try to find out if those non-counting patterns, that first-last harmony, if that was truly unlearnable, to see if that was like a hard limitation on the types of things that people can learn. So this was Regine Lai at University of Delaware in 2012. Regine Lai wanted to test the subregular hypothesis, the claims about the modularity of that system, by comparing the learnability of sibilant harmony and the first-last patterns. Sibilant harmony are tested. We know people can learn it because people do learn it. All the Navajo children learn it. First-last patterns are not attested, so it's a little bit up in the air whether that's accidental. Maybe it's just coincidence that no languages have this, or whether it's because there's some kind of hardware limitation in the human mind. And what Regine Lai found was that people learned the sibilant harmonic pattern, but they did not learn the first-last pattern. So that's nice. Nice small confirmation that maybe we're going in the right direction with this. Here's another interesting, like, tiny fact. I know that this graph is really hard. There's like a lot to unpack here, and we don't have a lot of time, so I'm actually going to just sort of gloss over it and just take my word for it. Like, people learned the sibilant harmony one. They didn't learn first-last, but what they did, which is really suggestive, is the people who were forced to learn first-last, they were put in that condition where they're exposed to a whole bunch of Shokososh patterns. They generalized to sibilant harmony. Even though they were exposed to stimuli that violated it, they still wound up generalizing to it, which says something really interesting, I think, about the learning process and about error forgiveness and statistical learning that we would probably want to cycle back around to at some point and investigate. Actually, Hutong Dai in the linguistics department is considering this for like part of his dissertation, think about how people learn even with bad examples, which I think is really interesting. Okay, so this is the story so far. We have a tool set that we can use to describe patterns using formal grammars. The subregular hypothesis is claiming that really only a subset of the regular languages that are actually learnable. And we do at least have a small amount of evidence from some prior artificial grammar learning that seems to confirm this. There's also a lot of other artificial grammar learning studies that find people can learn patterns that fall under this domain. But Regine Lai is the only one I know of that tries to push it upwards and fails, which is nice. So we know that strictly local patterns are learnable. We know that strictly piecewise patterns are learnable. And it seems that first-last patterns are not learnable, at least by conventional means. So something that I'm particularly interested in is the ways in which learning changes brain activity and brain structure. So we know that like being exposed to a language is going to produce some kind of neural change, has to implement knowledge somehow. And that will affect, your future processing. So once you acquire a rule, that should affect the way that you process new words. You should be able to detect violations reliably, and we should see some kind of brain activity that corresponds to that. So this is something that we've been doing, is induce learning of these phonotactic patterns using artificial grammar learning in the lab. You expose people to positive examples in the hope that they will generalize to the underlying rule. They'll get the grammar. And then you can expose them to violations and see, do they reliably detect violations? So this is our goal, is we want to measure these neurophysiological correlates of learning and phonological processing to try to answer some of these questions about what kinds of computations the machinery we have is well equipped to do, and what kinds of computations it's not well equipped to do. These are some of the questions that we've considered so far, like how do learners represent the patterns? This, I think, is a big deal when we think about mental representation. I think mental representation, to me, is still one of the main core computational goals in cognitive science. What are the representations? How are you representing information? And here we have, we're going to see there's some representational choice. You can sort of choose how you want to represent the pattern in these kind of restricted laboratory settings. So it becomes a meaningful choice that we can sort of see the effects of. And then we want to see how that representational choice affects learning. How does it affect learning and how does it affect processing? Because they're going to wind up with very different commitments. And also we tested whether explicit and implicit learning lead to different measurable types of neural commitment, different kinds of implementation of the knowledge that we think you're supposed to attain. So if you let people learn it on their own with no negative examples versus if you just tell people up front what it's going to be, how does that affect the way they process it afterwards? All right. So talk a bit about what it looks like when you have a rule. How do you like detect violations of that rule? Haven't yet talked about how you actually go about acquiring a rule from positive evidence, given the formalisms that we've talked about so far. And this turns out to actually be a really tricky problem. So one issue is if I give you a single word, let's take these two words here. These are both examples of words that obey sibilant harmony. They have two S's and they don't have any S's. These are good examples of sibilant harmonic words, sasako and sakaso. And so far the experiments we've done, this is sort of the format of the words that we're working with. They're 3-syllable words. They've always got 2 sibilants in them. The placement of the sibilants might vary. And we can think about trying to represent the rule here in 2 different ways. We can represent it with substrings. I know earlier I said you can't do that for sibilant harmonic patterns, but if you have a really limited input set, it's just words that are exactly 6 symbols long, you can't actually do this with substrings. It just might take a lot of substrings to do it. You can also represent it with so both of these can be represented with substrings. They can also be represented with subsequences. If this is your input, the one that has the S's kind of close together, right, in adjacent syllables, the prohibited substrings can be pretty short in order to capture the pattern. You only need a K factor, you only need a window of 3 symbols in order to capture both of those S's and see them both at the same time. So essentially a K factor that you need in order to do this with substrings has to have a minimum length that can capture both of the symbols that have to agree with each other. So the substrings for the word on the left, for the sasako, it can be pretty small, K factor of 3. But for the word over here, sakaso, because the symbols are separated by like 2 syllables, 5 symbols, now you need a substring of length 5. Your K factor is a lot bigger. And this is going to lead to a really meaningful difference in terms of like how much you have to keep track of in order to actually generalize what the rule is supposed to be. But in both cases, you could just instead keep track of subsequences. And if you're just tracking subsequences, then they're equivalent because distance doesn't matter. So what we're looking at here is a difference in terms of the dependency length, the amount of distance in terms of the symbols in the string between one sibilant and the other, the things that the rule cares about. And when you manipulate length, that's really going to change the implementation if you're tracking substrings, but it's not going to change the implementation at all if you're tracking subsequences. And this is why we say we think this is probably a better candidate for how this actually works in human beings. It just seems better. Your words get longer and longer, but you don't have to remember more stuff. Makes sense. Of course, we don't know if people are actually going to do that in the laboratory. But let's cycle back around to this induction problem, right? How do we learn a rule without negative evidence? I think this is a big problem actually for this. So when we think about how you detect violations, you have a list of prohibited substrings or a list of prohibited subsequences, and that's what you use to like sort of look out for stuff that violates the rule, right? You're looking for those prohibited things. The question is, how do you figure out what goes in that list? All I ever give you are examples of words that don't have any violating things in them. So how do you figure out what's supposed to go on the violation list? It has to be like all the stuff you didn't see, right? So like, how do you compute what the set of all the stuff you didn't see was? Well, first you got to compute the full set of everything you did see. So you have to track all of the substrings or all the subsequences that there are in all of the data that you're shown. Then you have to build, I guess, a hypothesis space of what all of the possible substrings or subsequences could have been given the alphabet and the K factor, and then look at which things from this list are not present on that list, which is a huge amount of work. It's a huge amount of work to do, and it's going to really matter how you're representing the patterns because it's really going to matter like how much stuff you actually have to track in order to figure out what's not on the list. So one of the interesting things here is that the search space grows at different rates for strictly local and strictly piecewise patterns, depending on the word length, depending on the dependency length, how far apart the things are, and depending on the alphabet size. So all three of those things can affect the growth rate of the search space in different ways. Here we're keeping the alphabet constant. It's a very small alphabet. The only thing that we're really changing is the dependency length. So it's how far apart are the two S's in the word. And if you're just tracking substrings, let's see, if you're just tracking substrings of length 3, you're going to have to track 30 things. If you're tracking subsequences of length 2, you've got to track 47 things. For the longer words, the subsequences increases a little bit because it increases for word length a little bit. But if you're tracking substrings of length 5, it goes from like 30 for substrings of length 3 to 400 to track the substrings of length 5. It's an enormous increase in the amount of stuff you have to keep track of if you're really committed to trying to solve this problem with substrings instead of subsequences. Does this make sense so far? Okay. So I think that like this problem is probably a lot more tractable if you assume when you go into it that I should probably just track subsequences instead of trying to keep track of all the substrings. And so when we put people in the lab, we wanted to measure their brain responses after they acquire this grammar, once they're exposed to the language. And we have a couple hypotheses, right? There's two sort of competing hypotheses. If people are making an assumption that they should track substrings, if they assume that the pattern is strictly local, then we think that the learning will be a lot easier for the shorter words and harder for the longer words, right? It's that dependency length. How wide of a window do you need to capture both of the segments that you need to see at the same time? But if learners are assuming strictly piecewise, then we shouldn't see any difference between the two groups because you track exactly the same stuff. The dependency length doesn't matter for strictly piecewise. And for that, we're going to look for a couple different ERP responses. We're going to look for P300, which is related to like categorization. When people are trying to categorize things and make a decision to push a button, generally we see a P300. And we've also seen from some previous studies in artificial grammar learning that you get this late positive component when people detect anomalies or violations of patterns that they've learned. And it's really analogous to the same kind of brain response you get to seeing violations in your native language. So these are the two things that we're looking for. And if we see a difference in these brain responses across the conditions, that might tell us that people are implementing the two. If we see a difference, then that would show that people are maybe making a strictly local assumption. Whereas if we see no difference, then maybe people are converging correctly on the strictly piecewise representation. So we've got two groups here. We've got a group trained on short words and a group trained on longer words. This is a really simple paradigm of just, we have people do listen and repeat training. They're just exposed to positive examples. You're going to hear words like shikishish and sakasas, and you just have to repeat them. And then after that, you're going to go into a testing phase where we put the EEG cap on, and then people have to do a task where you're going to hear new words that you haven't heard before, and you have to tell me whether you think they fit that pattern or not. I didn't tell you what the pattern was, so that's something that you have to figure out during the training phase. And so the only difference here is whether the words that you're exposed to are short or long. And there's a lot of variance in accuracy. This is actually D-prime because we did this in like an oddball paradigm. So people are hearing lots of grammatical stuff and then occasionally something ungrammatical, and you got to go, okay, that's bad. Mainly because we don't want to undo the learning by giving them too many ungrammatical examples in a row. Yeah.
Do they get feedback?
They do not get feedback. There's no feedback. So we do see a difference between these two groups. The short words, people seem to do better with short words than with long words, but kind of notice in this breakdown that like actually a lot of people are not doing very well in both groups, and you just have some people who do really, really well with the short words. And that's a little bit attenuated for the longer words. So there is an aggregate difference, but in general, people are just not very good at learning these things in the laboratory setting. I've ever told you this, artificial grammar learning is kind of hard to do. People don't really like doing this. But whatever, we squeezed a little bit of learning out of these people. We're really interested in though is what the brain responses look like. And we're interested in those two brain responses in the P300, which we measure from here. It's about like the center point of the scalp, and then the LPC, which is measured kind of in the back posterior region. And we measure the brain response to the grammatical words, the words that satisfy the pattern, and also the words that violate the pattern. And when we do that, for this short word group, we see a nice difference. And it's peaking 300 milliseconds after the violation point in the word. So we time lock everything to the onset, and then you can add a couple hundred milliseconds. So the brain response is peaking 300 milliseconds after you would have detected that violating symbol in the string. When we look at the other group, the long word group, we get basically nothing. So there's nothing happening here. They're for some reason not getting the P300, probably because they're just not doing very well and they don't know which ones are and are not grammatical. And we see something similar for the LPC. We see a positivity for the short word group, and for the long word group, we see basically nothing. They're not getting anything here. And this is an indication, combined with the behavioral data, it really looks like they haven't internalized this rule at all. They just didn't figure it out.
How many trials went into that? Those are averages of lots of words. Right?
Those are averages of lots of words and lots of trials.
But
Yeah.
very different numbers of words between groups, right? Because you said the pros are premium feedback.
Well, it's the same number of trials across the groups, but the words are different lengths.
But the correct and incorrects are. Did you say there were fewer incorrect words presented than correct words?
There are fewer incorrect presented than correct.
So
Yeah.
on any individual graph, then.
Oh, I see.
Expected the blue lines to have less signal to noise because they're the average of a smaller number of trials.
Yes.
But I don't.
Huh? But you don't.
But I don't see a higher noise on the blue lines than the gray lines. So that surprised me a little bit.
Yeah. We do some filtering for data presentation, which smooths things out a little bit. But that's true. That's a good observation.
Okay. Making sure I understand what I was saying.
Yeah. Yeah, that's right.
Right. And this is on the order of like hundreds of trials being averaged?
This is on the order of hundreds of trials. I can go back the slide. I think I have the numbers, the trial numbers. Do I have the trial numbers here? Okay, I didn't.
I just wanted to make sure I understood what I was looking.
It's in my pocket slides. Yeah, so this is the finding so far is when we manipulate word length, we do get very different sort of learning in these two different groups of participants. Seems that longer words are just really hard. And there are some questions we have about like, well, why is that? We really expected people to be able to learn this. It's kind of frustrating. So that, well, maybe there's like an L1 effect. These are English speakers. English doesn't really have any long distance phonotactics. So maybe that's why people are coming into this with the assumption that whatever it is I'm gonna have to learn, probably I can get it by just doing what I know how to do in English, which is tracking substrings. Could be just the hypothesis space for this got too big. Could be some kind of working memory capacity limitation, because this stuff also intersects with other cognitive systems. So at the moment, we don't know exactly why we don't get the brain responses or the behavioral results for the longer words than the shorter words. I think probably it's due to monolingual English speakers just being totally unfamiliar with this, personally. Okay, but I also want to talk about explicit and implicit learning. There's a little bit of backstory here, because as you can see from those previous results, like we wanted people to learn all of that stuff and they didn't. And so we got frustrated and we were like, what if we just told them what it was ahead of time? Like maybe that'll work. You just tell them the rule ahead of time. So okay, well then let's look at the difference between implicit and explicit learning. We'll just have group people, we'll just tell them what the rule is, and hopefully we could squeeze the right kind of brain response out of them if they just know ahead of time. But the two types of learning are really different. They wind up giving you different kinds of commitments, right? Because implicit learning tends to be kind of effortless and unconscious. You don't have to like think about what you're doing. It doesn't draw on like your central executive system usually. Also, it's this thing about not getting feedback and only having positive examples, right? So we're maintaining that. They're doing listen and repeat. They're only seeing positive examples and they're not getting any feedback. Explicit learning tends to be more rule-based, like you can just straight up tell people, this is the rule. Use your central executive system, please, to remember this so that you can, when I give you new things, you can interpret them. Here they're not getting any feedback during the training, so we're not actually doing feedback, but we are giving them, we're telling them what the rule is, and we do give them some positive and negative examples so they know what that sounds like. So the idea is maybe we can observe some differences in terms of how well people do at this task and what kinds of brain responses they get based on how they learned the pattern, how they were exposed to the pattern. So again, we're looking for the same things. We're looking for that D prime We're looking for a P300. We're looking for an LPC. And our hypothesis going into this was that implicit learning probably will engage your phonological processor better because it's an automatic processing module. It kicks in when you're a baby. Babies don't have to stop and think about, wait, mom, wait, what are the rules of the grammar of my language? We tend to think that like, if you could just sort of like tune out the noise and engage that module, that it will do what it does sort of automatically. Whereas with explicit learning, I'm just going to tell you the rule ahead of time, and it's like very intellectualized, and you're going to be thinking about it with your central executive system, and you're not going to engage that modular part of your brain that does phonology. So we think that maybe you can get stronger brain responses with implicit learning than with explicit learning. And for this one, we stuck people just with the shorter words because we know the shorter words works. People have a hard time with longer words. So same basic thing, we do training and testing. For the implicit group, it's exactly the same deal as it was previously. They're just doing listen and repeat with no feedback. But for the explicit group, first we tell them what the rule is. We have a little conversation with them about how this works, what it sounds like. And then they go through the same training and the same testing. And here we see a massive difference in the D prime. So the implicit group, they're above 0.5. They're still, that's a D prime that indicates they've learned something. It's greater than 0, significantly greater than 0. But the explicit group is almost 3 times higher. So the D prime is fantastic. It's like, wow, this is what we wanted to see. We should just tell people the rule all the time. Now they really know what it is. Question is whether it leads to the same kinds of brain responses. And this was the part that was kind of shocking, which was, yes, we see the P3 for the implicit group. We see nothing, nothing for the explicit group. And yes, we see an LPC for the implicit group, but we see nothing, nothing significant. You see something there that looks like, well, maybe that's a little bit. No, it's nothing. And this is really shocking. We're like, what? Just because we told you ahead of time, like even with that amazing behavioral data, they still are not getting the expected brain responses. We have a lot of questions about why that is. One thing we know, like, well, we're pretty sure they're using domain general cognition. They're probably not engaging that, that phonological learning module. Maybe they don't have to do any real problem solving. There's a lot of stuff that's kind of different in these two groups. We don't know exactly why that leads to these different patterns of brain responses, though. This is still, I think, a puzzle for me. A very quizzical look, John. I don't know. What do you think? It's strange. So this is the basic summary here, right? We want to know, how are people thinking about these patterns? Do they assume locality? Do they assume piecewise representations? It seems that our English-speaking learners are assuming some kind of strictly local representational strategy to learn this novel phonotactic stuff, probably just because of prior exposure to English patterns. And when we look at implicit and explicit learning, it does seem like, even though they're converging on the same kind of grammar, they are both acquiring it to some degree of proficiency. They seem to be doing so in very different ways, and that's giving us very different kinds of brain responses. And we think that implicit learning probably is leading to a better internalization of that, of the underlying grammar that looks more like native language processing, but we don't know. We also don't know, like, well, what if you test them again a week later? Would the implicit learners have better retention? We don't know. It's kind of hard to get people to come back. So we never actually tested that. But that's something that we might think about doing in the future. So that's where I want to talk about now. Like, where do I go from here? What do we do now? And I think this is actually a pretty wide open space to do a lot of really interesting work and ask really interesting questions, because there's not a lot of people in the space yet. So I've got to get on the ground. We are working on, I've created like my own little research group, and we're going to be using that shared lab space that we're sharing. Oh, actually, it's right over here that we're sharing with psychology. Russell is in my lab group. So we've been working on stuff, coming up with ideas for things we can do. And I have a lot of questions that I'm interested in. Like, well, first of all, the biggest thing is, what if we introduce a more naturalistic learning environment? Sitting in a room, in a sound booth, and listening to these fake words that have no meanings, that all have exactly the same length and exactly the same format, and just repeating them over and over again is really, really weird, and not how any human has ever learned a language ever in the history of human life. So I think, well, what if we do something a little bit more natural? What happens then? So one of the things we're thinking about doing is creating a new paradigm where we want a more full, more rich artificial language, where the words have meanings, there are sentences, it has morphosyntax. There's like a lot of other stuff that people have to learn at the same time. And our hypothesis is that if learners are unaware of the phonotactics of the language that they're learning, they're not thinking about the phonology. They're going to be thinking about learning what the words mean, and they're going to be thinking about learning the morphology and figuring out how sentences work. And maybe that way we can sort of tap into that modular phonological learning mechanism that'll just activate automatically while their executive system is distracted doing other things. And so we want to use something like this where we have a maybe some kind of like either picture or video sentence matching paradigm where you see you'll see a video of someone doing something and you'll hear a sentence like Tashinikish. Okay, so what does the sentence mean? This is only one example, but I think you can do it. I have faith in you. What does the sentence mean?
He's jumping.
He's jumping, right. And so you'll just get lots of pairs of things like this. You'll figure out, oh, okay, maybe this is a pronoun. Maybe this is a verb. It's going to have some kind of ending that's going to change depending on like, oh, how many people are there or things like that. And going to sneak in. You probably already see it. Very sneaky. Sneaking in the sibilant harmony. Hopefully people won't be paying conscious level attention to it, but they might learn it anyways. Okay, we have other questions we want to answer using this more naturalistic paradigm. I'm also really curious about the intersection of complexity and naturalness, which I'm noticing more and more people are starting to investigate, which I think is really interesting. Because complexity is only like one dimension of what makes stuff like this easy or difficult. You can also think about naturalness. Like there are certain kinds of things that crop up in languages all the time, and certain kinds of things that never do, that has nothing to do with complexity. It's something else entirely. So one way that this might affect this line of research is think about strictly piecewise patterns. Strictly piecewise patterns in general are really hard to generalize over large alphabets, and most languages have pretty large alphabets. But it becomes a lot easier, and like your search space gets a lot smaller if you can group sounds into natural classes and then just pay attention to those. So like I said earlier, remember it was like, you have to keep track of every subsequence. It was like sh, e, sh, in, sh, g, sh, da, 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 da. That's so much work. What if I'm only going to keep track of maybe just the sibilants? Maybe just, whatever sounds I think can like naturally group together. I'll just track those things. That cuts down my search space enormously. So I might have a pattern like this. We have the sibilant harmony pattern where the only thing we really have to care about are these things that form a natural class, all of the S-type stuff. But then I might do something like this, where this is exactly the same level of complexity, but it's super weird and no one would ever do this in any human language, right? So here I have another pattern where not only do I have to match the sibilants, I also have to match the sibilants to a liquid. So like if I have an S, it's also got to have an R. If I have an esh, it's also got to have an L. I can't have an R and an esh. I can't have an L and an S. These sounds have nothing to do with each other. And so it's not the kind of thing that we ever see in a human language. It's probably, my assumption is not the kind of thing that people are going to be very eager to learn. But it's an open question. So it's not any more complex. It's just weird. And I think the long-term goal is to try to find some functional specialization for this phonotactic learning in the actual neurobiology. This is something that's maybe like far down the road. But ultimately we do want to answer these questions about physical modularity. Can we find the actual neurobiology that's associated with the processing here? Where is this stuff actually happening in the brain? So yeah, that's the end of what I've got, right? Just that I'm really into sort of marrying these different approaches, taking formal learning theory, using it to sort of operationalize how we describe these kinds of patterns to give us a foothold on how we can think about the computations that are involved in this domain, and then see what kinds of predictions that might make about what we think is actually happening in a brain and in the mind. Okay, that's all I got. Thanks, guys.
Aaron's first suit.
I expect no less.
Was I called on?
Working on it, yes.
Yes, Karen.
Hey, Ryan, that was just absolutely fantastic, wonderful, et cetera, et cetera. I have a bunch of questions, and maybe I'll start with just one observation. So there's a well-known American phenomenon that if you're trying to learn a second language, the one area you just completely fall apart on if you do it as an adult is phonology. And I'm wondering if that has some things, whereas little kids do fine. And I'm wondering if that has something to do with your implicit versus explicit, teaching type phenomenon. Are you hearing me?
Yeah.
Yes, we can hear you. We just can't see
So
right
that
now.
was just sort of a comment. And since we have so many students who are heritage speakers of different languages, you may be able to sort of look at some of the things where English is putting in restrictions that make certain things hard that maybe for our heritage speakers, they wouldn't in your artificial learning things.
Yes.
Here's my-
Yes.
yeah.
This is
So
perfect.
here's my real question. There do seem to be languages where there are phonological restrictions that operate across words, right?
Yes.
So in all of your representations, you have hash marks to indicate the ends of words.
Yes.
So if a language allows, and I'm sure Arnold Histevik has talked to you about this, because in Norwegian, for example, there are certain phonological rules that cross word boundaries, not just syllable boundaries, but word boundaries. And how does that play into your sort of your story? Because if you don't have hash marks, I'm not sure this works. So they're neither strictly local implies hash marks between words, as does piecewise. So how do you deal with things like that? Do we just ignore all hash marks and it's just one long string of sounds?
So this is so perfect because I was editing these slides this morning and I was really agonizing about like, should I put in this thing? I was just this idle thought about, I really do actually want to tackle this question at some point about word boundaries. It's so funny that you brought it up because I was thinking the exact same thing the last couple of days. There is nothing inherent about this formalism, I think, that rules out rules that apply across word boundaries. And you do need the hash marks in order, I think, to make sense of this. But there's nothing about strictly local that says you can only look at things between the hash marks. You could have a substring that has a hash mark in the middle. And that would get you sort of like a window that could look at something that applies across word boundaries. So I don't think there's anything that rules that out. Obviously, like languages actually do this. So if the formalism did rule it out, that would be a huge problem for the formalism and I would abandon it. But I think that this is doable.
Okay. Yeah, that was basically what I was trying to figure out. The other thing I noticed about the language is that in terms of syllable structure, it's extremely simple, right? It's
Yeah.
CV, 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 CV. And I wonder if some of the restrictions like sibilant harmony are more likely to work in that kind of very simple languages, that very simple syllabic structure, as opposed to, I don't know, Polish or whatever, where the sonority hierarchy just gets completely thrown out the window and you got, 6 consonants doing unholy things with one another in sequence. So I guess the story I'm asking you is, within a language, yeah, all languages are equally expressive, or we're told to say that. But could it also be that within languages, there's sort of a level of phonological complexity so that we won't violate beyond a certain point? So if you've got a language where you've got this kind of sibilant harmony, it's going to be pretty good and have nice syllables, right? Not do the crazy non-sonorant type syllables that other languages have.
It's a hard question to answer only because we only have, like our sample size for sibilant harmony is 2.
Yeah, yeah.
And those languages do have, in like global sense, they do have pretty simple syllable structure like CVC stuff. There's not a lot of clustering. That's a good question about whether that matters. So actually, this is a question I've been curious about for a couple of years. And that has to do with syllable structure and how there's another question about representation, right? So you can think about representing strings and or subsequences and like searching across the whole space of the syllable. But something occurred to me, which is we see a really big difference in our participants when you go from 2 syllables to 3 syllables. And I was thinking about that, like, Well, 2 syllables is like kind of local on the syllable level, right? They're adjacent syllables
Right.
versus non-adjacent syllables. So there's a possibility that people are actually using the syllable as sort of the underlying unit for their search space or their representational schema. And it's when you go from 2 to 3 syllables that like wacky things start to happen and accuracy falls off a cliff. And that's something that is potentially testable, right? We can manipulate the string distance versus the syllable distance really precisely by changing exactly what you're talking about, having more complex syllable structure. So you can have longer strings, but with the same number of syllables versus more syllables, but over the same length.
Right.
And that's something I'm very curious about too.
Yeah, the first thing I thought of as you were presenting the work when you're talking about local strings was wiggle phones, from the original past tense generalization. They only worked because, so McCullen and Rumelhart's work on the past tense. So the first, connectionist story that supposedly did away with rules for, why kids said, go. It only worked, according to Alan Prince and Steve Pinker, because they had these representations of 3-letter sequences. So you take the word like kicked, and it would be K-I-K, I-K-T type thing. And I was wondering, to capture English, what K factor is the most efficient?
For the phonological rules of English?
Yeah.
Yeah, that's a good question. I have to sit down and think about like, what are all of the rules of English? You're probably not going to need a K factor greater than 4.
All right.
Most things are just going to be 3.
That's what I was thinking. That's what I was thinking. It's probably 3. But anyways, great talk. I'm looking forward to seeing each other in person more and maybe sharing the shared lab space. But this is so cool because it's, and I'm liking that you're thinking about moving into morphosyntax, a domain I'm a little bit more with.
Well, okay, yeah, I actually talked to Russell because he really wants to do negation stuff. And I'm like, hey, throw it in the language, like whatever. We're building a whole language anyways. Throw the negation stuff in and it'll be like fillers for, this experiment, but it'll be viable data for the other experiment.
Absolutely.
Oh, Jane.
Jane?
Can you hear me?
I can.
Okay, fabulous, very exciting. I'm going to try and make this kind of short. Basically, what you're asking people to do, right, is not first language learning, right? It's second, third, whatever language learning. And we know that that is different. So I'm wondering, first of all, how do you get around that? Right? Because if you're going to do this study with adults, it's always going to be that way, no matter what you do, right? And then the other question that I had is, we know that like even by infants that are learning more than one language behave differently when shown a new pattern like this than monolingual infants do, right? Basically, monolingual infants are more willing to be like, okay, cool, whatever, I see this pattern. Whereas infants that are learning more than one are like, I'm going to hold off on my judgment of this because I don't know. I know that I've got multiple different possibilities going on. So the first question is, how are you going to get around the fact that you're kind of talking about second language learning? And the second question is, could we do this? Could you do this with people who are already bilingual, right? And obviously, well, probably they're not going to be bilingual in Navajo or Chumash, right? So then see how they do.
Okay, question number 1. How do we get around the fact that this is really L2 acquisition? Yeah, I mean, I'm just gonna be upfront. I don't really want to work with kids. So people often ask that, like, hey, what if you did with kids? I'm like, hey, what if you did it with kids, huh? I don't do that. But like, totally, if anybody wants to do this with kids, please do it, because there are like really interesting questions here about how children acquire these patterns. That's probably more informative than how adults are doing it. I still think that there's something we can learn from seeing adults do it. And I still want to see if like we can get that kind of native-like acquisition in the lab with adults. We've seen, enough artificial grammar learning studies to see like people do, they converge on the right kinds of grammars under these conditions.
Yeah.
It's just a question of, are they doing it with the right mechanisms that we're actually interested in?
Yeah.
And that's why it's interesting to look at the difference between like things that we know are learnable and things that we suspect are probably not learnable, and then see a difference. But yeah, that's a good point. So the other point was about like using children who have a different background, different like language experience, or using participants with different background. And this is actually something we've been planning for a while because my original collaborator on this is Turkish. He's a native Turkish speaker, and Turkish has long distance phonological patterns. They have a really pervasive vowel harmony. And so this was always a question we would get, like, well, what would this look like if you did with Turkish speakers instead of English speakers? So we have that kind of like on the back burner. He's really busy, but I'm like, at some point he's going to I'm going to keep pushing him, like, get me a population of Turkish speakers who could do this. Maybe we'll run something online, see, like, maybe they'll learn this way better because they're already sort of primed to think about long distance phonotactics to begin with.
Yeah, that's a really cool prediction. That's awesome.
Yeah, right. That would be really interesting to see. Maybe they're just way better at it.
Yeah.
I suspect that's probably true. Yeah, John.
I'll just be loud so they can hear me. So I'm fascinated by the implicit explicit difference. And one thing that struck me as I was listening to the talk is that I wasn't sure in that moment if it mattered that you were doing words or phonemes at all, or if it could have been a sequence of tones or even a sequence of lights.
Yeah.
The difference obviously is that they can't necessarily reproduce those. So you'd also be changing the hearing versus production dynamic. But I was wondering what your thoughts were on that.
Regine Lai actually did this. I think it's part of her dissertation where she replicated that last sibilant harmony study with musical instruments, drum beats versus whatever. It's like different, timbres of things, but also different. So it's like there were like 2 dimensions of things that can vary, and you have to like sort of match them. It worked exactly the same way, but with different stuff that was non-linguistic to see if you get the same kind of learning. And I'm trying to remember what she found. I think that it didn't work. I don't think she did. And I think it wasn't published because she didn't get like the results that she wanted where people didn't really learn it.
Music certainly does have those long distance relationships.
It absolutely, yeah, it does. Right. I have to go back and reread that now. I hadn't given a lot of thought to it because I'm really fixated on like one domain. But it's a great question, right? Like, because music does overlap a lot in terms of its complexity with language. It has very similar properties.
And it's sequence-based. And
it's
sequence-based.
sequence-based.
Has resolutions to patterns.
And we know that there's like some shared underlying neural machinery for both of those things. So it would make sense. Yeah, that's a great question. We could try this with lots of different things to see what works and what doesn't work. It's taking me a little bit in the opposite direction, trying to make it a more natural language learning environment. But it's really interesting. Okay. Is that it?
Any other burning questions?
Great job, Coach Ryan.
Thank you.
Thank you for coming, everyone. Let's see.
Bye.
Bye.
Bye-bye.
Can't actually see how to pick.
Where's the honors? No, I don't think so. Where's the honors?